Hey James, thank you for coming in and doing so much. Your work is incredible. Your background is incredible, and you're the dean of physical sciences and professor of physics and astronomy at the University of California, Irvine. You're a researcher, a par excellence, a member and former chief of the James Webb Space Telescope User Committee. You serve on the Space Telescope Institute Council. You're the mastermind of this new kind of project. I don't know if we could talk about that. You also helped launch the UCI Eddelman Quantum Institute. I just finished the Forbes article on 11 top experts in quantum. So
Oh,
I quoted
fantastic.
them. So I'm going to
Yeah.
add you to that list in the future. And, you're definitely sort of the center, the hub of so much. So thank you for coming in today and sharing all of that excellence with our audience.
Well, absolutely. It's wonderful to get a chance to talk with you today. Really excited.
So, my audience is quite mixed. I have scientists in the audience and notable experts and practitioners, and I also have CEOs and investors and things like that. In fact, interestingly enough, when I do posts on LinkedIn, usually the number one, because I track the metrics, it's like CEO or founder or the top two. So I do definitely have a CEO audience. But my audience in general, they'll be inspired by your background, your career, because you've done so much. And so they'd be interested in, what were the inflection points in your life? Maybe it's when you're young, or
Hmm.
maybe when you're teens. It could be when you're in school, or maybe afterwards, or a combination of that. Let's say two or three inflection points, which really inspired you and made you this amazing scientist and person that's out there today doing so much.
Well, sure. I'm happy to take a stab at that. I think it's useful maybe to start as a kid. When I was younger, I've always kind of been interested in science and math, but I was a really big fan of Carl Sagan. I remember him being on PBS, and the thing that I found really compelling about Cosmos and just his viewpoint was this very global but also cosmic perspective, really getting out from our own heads in some sense. How do we fit into the universe? These really big questions about why we exist, why we're here. And I mean, there's something very compelling about if we think of the Earth, our planet, as a small pale blue dot, as Carl Sagan said, in this vast universe. I think it brings us closer to each other as humans. We are this species that's done this remarkable thing. We're only 100, 200, 100,000, 200,000 years old, right? And we live in a universe that's 13.7 billion years old. That's much, much larger than anything we could sort of experience day to day. And yet we've figured out so much. And here we are together on this little speck of dust in the solar system, and we're hanging together and trying to appreciate this wonderful globe that we're on. So I think even as a child, that perspective has always stuck with me, and I think it's motivated me to sort of think about, well, what are the biggest, most interesting questions that we can tackle, and what do we need to be doing to bring each other together and work together towards even more thriving in the future. So that's definitely a part of it. And I think that's what got me on the track of studying physics and eventually astrophysics. And, I'm a cosmologist. That's why I was interested in things like the origin of the universe and how we got here. But, I think coming to UCI was pretty transformative for me because it gave me the chance to not only interact with an incredible group of astronomers and particle physicists here on this campus, but as being part of the University of California system, I got an amazing opportunity to interact with colleagues on all the other campuses in astrophysics and cosmology and physics. And it really opened my eyes to sort of a breadth of approach that we can sort of do things together and build systems of scientists to work towards large and big problems. And it got me interested in academic leadership roles where you can try to play a role in facilitating things that maybe otherwise wouldn't happen. So you can get large teams of people together to do major initiatives in astronomy, or to do things with internationally preeminent telescopes that otherwise couldn't be done and cannot be done by a single person, but just require large teams of people all pushing in the same direction to discover things that can't otherwise be discovered. And I think that's influenced me in why I've worked with the James Webb Space Telescope and Hubble's telescope, and even in the UC system with we used to run a center on galaxy evolution here. So I think that's another sort of phase change. But when I became dean of the School of Physical Sciences here at UCI, it was really my job to sort of think about, what are we doing here in physical sciences more broadly, and what's our mission? And, perhaps the most compelling story I can tell about this role is that, the founders of this school, including Fred Reines, who won the Nobel Prize for discovering neutrinos, but also Sherry Rowland, who was the first scientist to lead efforts that won a Nobel Prize in climate-related science for his discovery that CFCs deplete ozone. Sitting in this school and thinking about what the mission of this school is, there's a big chunk of it is to do fundamental research that tangibly improves the world, improves the lives of people, and to use a scientific understanding to drive regenerative activities more broadly. And so I think that has really lit a fire under me, that sort of legacy of excellence here, thinking big, thinking globally, to try to see what can we do as a globally preeminent institution in a large and thriving state, to do what we can to tangibly move the needle on this crucial problem of climate change. And so I'm focusing a lot of energy on that right now.
That's really fascinating, from Carl Sagan to UCI to, you joined UCI in 2004, and then you became the dean in July of 2019. So that's kind of a journey. And one, as you mentioned, the sort of interest in science and the confluence of all these different areas. You mentioned that your school has these Nobel Prize winners. You have 3 Nobel Prizes within your group. 1 in physics for the discovery of the neutrino, 2 in chemistry, and the first for the discovery of the role of chlorofluorocarbons playing in the depletion of the ozone layer, and then most recently for developing organic catalytic chemical synthesis methods to aid in the development of new medicines. It's just really, really, really interesting. Can you talk about this idea of bringing together all of these different schools within UCI and your vision for that? And
sure.
And
yeah.
I know some of that maybe you can't talk about it yet.
Well, I could definitely tell you about sort of the vision, and it's a vision that I think a lot of people on campus share. And the details aren't worked out yet, but I think this vision is something I can talk about. It's basically this, we're facing this global issue associated with climate change and environmental sustainability. I don't really like to use the word crisis, but it's certainly a situation that we need to pay laser focus to, right? In this problem, because it's global in nature and infects every aspect of how the world works and the human experience, is no longer the domain of physical climate scientists alone. I think the heart and soul of it is physical climate science. And, that starts in our school. We have the first Earth System Science department in the country, founded by Ralph Cicerone, who was a friend of Sherry Rowland's, an atmospheric chemist who had this vision that in order to really understand what the climate's doing on Earth, you have to think of the Earth as a system. There's people, there's water, there's oceans, there's the atmosphere, there's animals. This is a system it's very complex and is interacting. And to understand what's happening in the globe, you really need to think about it in this very interdisciplinary way. But even more so today, every single school on this campus, from the law school to the business school, to people doing policy, to doing biology, and certainly engineering, information computer science, physical sciences. So this includes chemistry and physics and earth science and mathematics. Everyone is thinking about how climate change is affecting the world and what we need to do about it. There's not any really forward-thinking business community that I'm aware of that's not thinking about, okay, what are we doing in a world that has accelerating climate change, right? What are we thinking about in terms of policy implications for understanding how do we navigate the future in a world where things are changing, where the risk of fires is higher, or air quality, et cetera. So in recognition of this, we're trying to come together as a campus to have an all-in response to think about how we can work together to tangibly move the needle on climate change in a way that really scales globally. In order to do that, I think there's a recognition that we can't be an ivory tower that's just, pontificating to the world the way things should be done, but it's really more of a porous nexus where we can try to be a neutral convener for people coming in from the private sector, from NGOs to government agencies, to policymakers, to thinkers, futurists, everyone, to begin to think about what can we be doing in this area that really tangibly moves the needle in this space. And I should say education is also key to this. So as an educational institution, we want to play a role in sort of educating the next generation of sort of leaders in this space, whether they end up on, doing business or engineering or whatever, they have some deep understanding of what's happening in a world with this accelerating climate, and they can adjust and lead through that change.
That's kind of fascinating. I mean, you alluded to this earlier. I mean, the law school, different other schools that are part of this, together with the traditional academic departments of chemistry, physics, and astronomy, earth science, and mathematics. But you've got something like 16 schools. Are they all engaged in this idea that you've got to do this interdisciplinary, sometimes they call it transdisciplinary, multidisciplinary coming together to address this issue? And then I think you again alluded to that you don't think there's anybody else doing this right now, right?
I'm not aware of this kind of all-in approach that really is framing things this way. I mean, I'm sure other people are thinking about it because it's sort of natural to try to figure out how to bring people together. But yes, that's right. Every school is involved. Leadership of every school is supportive. The other aspect of this that I think is quite unique is it's not actually, just every academic unit. It's not just the sort of educational enterprise, but it's also sort of from the facilities side and the side of campus where, if you think about it, we're basically a city. We have some 30,000 people inhabit this campus. So it's like a small city. We have our own power grid, which is interesting about this campus. We sit on our own power grid. We order lots of food. We have transportation issues. We heat and cool our labs and our buildings. So thinking about the campus itself as a laboratory for climate solutions that scale at the size of a city, that's also interacting with the power grid from the outside, with our internal power grid, with our own solar panels, with distant solar panels, with how we're going to store energy from day to night. Those are the kind of activities that we think can be unique, because we can treat ourselves as a laboratory for exploring solutions that may work or may not work, and begin to figure out how to then scale that up to other city-sized entities around the country, around the world.
What fostered this idea that you've got to be all in and working together and so on? Is it because of all the data that you're seeing? I mean, is there some trigger points for you or flags that were just too compelling that you said, you know what, we have to address this in some way?
Well, I think the thing that's pretty interesting, right, is we've had a number of activities on campus where we're trying to bring together folks who care about these issues. And this started with a group that we call Solutions That Scale, that started very organically with professors that just kind of ran into each other, at a coffee cart and said, we really need to do something big here. And it started with a core group of people that are a little bit more on the STEM side of things. But as time went on, almost by, a friends of friends kind of situation, a larger and larger group of dedicated faculty began to come together and say, this is what I'm turning my research towards too. And really there's this environmental justice angle that we need to think about if we're going to restructure the electricity grid and the power grid of and the energy grid of this country. We have to think about what that means for disadvantaged communities and and privilege, et cetera. So it just began to kind of become obvious that there were so many different pieces of the campus that had something interesting and important to contribute to this problem. It's not a world where, it's just going to be engineers who fix this problem, because if you're not consulting, people who are really talking with folks out there in the community and the business community, et cetera, you're going to fail. You need to have this broader vision, the 30,000-foot view of the situation to really enact things in a way that's functional. So I don't know if there was any specific tipping point, but I think the realization was, if you had meetings around this topic, you had folks showing up with important things to say from every corner of the campus, from the undergraduates to the professors in all the different schools.
I work a lot with investors and with other groups where we monitor globally, what the situation is, and then we try to do good work for global impact in a good way, right? So, and I guess the model being for the benefit of Earth's ecosystems and also for the benefit of humanity. So much broader than just people, because everything is influenced by this. Do you consider then sort of the Earth ecosystem almost like a living entity in some way, and in an abstract way, and that's where we have to come to the aid of what the situation is? I mean, what's that meta view of the world and climate and where we are today?
Yeah, I think that's a very useful way to think about it. The Earth is, humanity is certainly a major player. And we are affecting the globe and the globe's climate in a way that I think is kind of unprecedented for a species of our size and in the period of time we're doing it. It's not the first time in the history of the globe that this has happened, but we know it's happening. The thing that's different about us is we recognize it's happening and then can do something about it, right? But it's certainly true that every aspect of the Earth system, the biology, all life, it plays an important role. And, phytoplankton in the ocean are doing, most of the heavy lifting in creating the oxygen that we breathe, for example, right? So it's a complex system. We have to think about it that way. We can't think about it in isolation. And there's a view in which the Earth, can we regenerate this globe where all life on Earth begins to thrive? Because it's not just human life. If other parts of the ecosystem begin to collapse, it's bad for everything. It's not just us. The 500,000-year time scale, the Earth's going to be fine. Whether we're here or not, the Earth's going to be here, right? We're much more concerned about the 100-year, the 1,000-year time scale where we hope we're here and we're thriving with the other species that we've evolved to live with.
So I'm going to be a little bit more fluid now, reaching into your past and then integrating that with your current work and future work. And so it's going to be very fluid. and just a reminder to the audience, these interviews are unscripted, so James is not prepared for this. But just looking at your background, you oversaw the recruitment of all of these new faculty members and the establishment of the UCI Center for 2D Materials. Can you talk about that?
Sure. I think key to this understanding, let me back up. I am a firm believer that the science and technology are a force for good in the world. And at least they can be if utilized appropriately, right? It's not to say it's the only force for good in the world, but if we are to sort of thrive, I think, as a species going forward, I think science and technology has a really fundamental role there, right? And so the Center for 2D Materials is about thinking about really interesting quantum phenomena that could happen on sort of the scale of sort of one, atom thick materials or two atom thick materials, and what interesting properties can happen as you begin to understand the physics on that very sort of quantum scale. And there's a belief, right? And I think a well-founded belief that the next technological revolution that we will experience will be in understanding the quantum world at that level. You talk about designer materials. Can you design materials that are light, that can absorb energy and utilize them in some effective way? High temperature superconductivity, incredibly high memory storage devices that require very little energy and are extremely small, et cetera, right? And so as we invest and think about the next generation of sort of what we're going to need to thrive as a civilization, in the next 100 years, it's that core fundamental research that we think, will drive it. Much like, the early days of quantum mechanics in the early 1900s and early 20th century eventually drove, transistors and the technological revolution, the huge boom that we saw with technology in the late 20th century and early 21st century. We anticipate those kind of fundamental advances will drive incredible technological advances, in the next 30 years or so.
I mean, did you look at things like, or is, I don't know how connected you are with the group now, but things like pristine graphene, or, these quality particles like Microsoft and their work on topological materials and things like that, right? Topological quantum effects. Do you have any views on things like that?
Oh, yeah. I mean, so this 2D Materials Lab, a couple of our professors who work in there were sort of the original people who, as postdocs, were some of the people who led those foundational papers where, you sort of twisted graphene and suddenly it was conductive and then it's not, those are the people who did the work now are sort of standing up their own labs here at UCI. And so we're very excited about where that might lead, and sort of, tunable things that you go from you go from a conductor to, an insulator just with a twist. So yeah, I'm very excited about those directions. I mean, I think always with fundamental science, you think this could really lead to something major. We're going to keep trying to figure it out. And, 1 in 10 times it does, or maybe 1 in 100 times it does. And when it does, it's incredible. And sometimes it's just a gee whiz. That's really interesting physics. Not sure what we're going to do with it. And that's kind of where we are now. I think this is why I think government funding of fundamental research is so important, because sometimes you have to fund things and, you strike out in terms of technology 9 out of 10 times. But when you get that grand slam, it means everything. So yeah, I mean, that's the attitude that I have. I think it's regardless of what happens technologically with a lot of these discoveries, we're learning a lot of really interesting physics. And there very well may be some, tangible payoffs that really transform the world, depending on what we figure out what to do.
Now, this is related because it's all about quantum science, right? Or related to quantum science and or quantum science and technology. There's an idea, or quantum information science and technology, QUIST. You helped launch the UCI Eddelman Quantum Institute. And what are the curious problems? What are the things that you're looking at in that institute? And, not just today, but where do you see as the big questions that you want answered? And then do some crystal ball, what questions will be answered?
Right.
Let's say in 2 years, and let's say by 2000.
Well, I would say that there are a number of steps here. And when you talk about quantum science, you could be talking about different things. You could be talking about interesting materials, sort of quantum materials, quantum sensors, using qubits to measure things you otherwise couldn't measure. But you could also move towards quantum information and quantum computing and sort of, the ultimate goal of incredible computing. There's another area, in addition to the sort of 2D materials space that we have great expertise in here. There's a couple other areas that we're sort of doing interesting stuff. And one is in an area called spintronics, which is where you're thinking about using, in traditional electronics, it's the charge of the electron that is effectively doing things, right? But in spintronics, it's not the charge of the electron, it's the spin of the electron. It's the quantum spin. Each electron can either be an up or a down state. And in principle, you can store information with that spin. And it requires a lot less energy to flip it than it does to sort of move an electron around, and generates a lot less heat. So there's a goal that maybe spintronics will be a very interesting way of thinking about doing computing and data storage, et cetera, in the future. As we move towards quantum computing, for example, an area that we have a great expertise in is in computational efforts, classical computational efforts to understand materials. So we have a deep expertise in how you simulate sort of conglomerations of atoms and what these materials are going to do when you put them together. And one of the sort of, hopeful, obvious use cases for a quantum computer when they are built is simulating materials. Simulating quantum systems with a quantum computer, in principle, is what you want to be doing with a quantum computer. That's a really great use case. And our role, we think, may be in actually not building the quantum computer, which a lot of companies and deep pockets are trying to do that with different technologies. But an interesting thing to think about is, what are we going to do with the quantum computers? What are going to be the most interesting problems to try to tackle when we get there? One thing you have to do is test the quantum computer, right? So if you're doing calculation with the quantum computer, how do you know if you got it right? So there's going to be obvious test cases that you need a classical computer to run this simulation, and then the quantum computer does the same simulation. And you want to make sure the quantum computing is actually getting the right answer before you then utilize it for a bunch of stuff, right? So if there's a role there, I think, as we begin to sort of build out this structure, those will be the first few things we're going to do. The other thing we're trying to do with ECI, which I think is important if you think about it, you know this, but UCI is a really interesting campus. We're incredibly diverse. A majority of our students are the first in their families to go to college, and yet we're functioning at a really high level as a research institute. So it's this very interesting mission-driven aspect. And what we feel as an important mission for the Eddelman Quantum Institute is to educate the next generation, the quantum workforce. This country is going to need a bunch of really well-educated people to step into these companies and begin to run these quantum computers or build these quantum materials to create this technology. So we are building programs in quantum science where you can come in as an undergraduate major and be ready to sort of step into those roles. And so that's an aspirational goal of ours that I think could really have the biggest payoff of all, because in terms of the number of students we could be educating every year that then go off into the world and thrive and invent new things, I think that's going to be another role we can play in addition to sort of the core research that's being done in the laboratories.
Yeah, and if you look at the new act that was signed in August, the CHIPS Act, there's funding for this, right? The education side, or the building a skilled workforce for quantum computing, or quantum information science.
Yeah, the timing is very excellent. It's excellent. I mean, we sort of are reading the tea leaves and kind of thought that some of this stuff might be coming down, but the timing is excellent, and I think everything's well aligned. I mean, this is not a secret, right? People who are paying attention know that this is really the future, and so we're trying to prepare for that and make sure our students are prepared for it too.
It's interesting. In 2015, I was asked by a group of CEOs that represented almost 100 trillion in assets under management, just 100 of them, by the way. And the GDP of the world was about like 60 trillion at the time. So it's like 1.7 times the GDP of the world or something. And they said, Stephen, can you look 10 years into the future and tell us the things that we need to look at now? Because we don't want to get caught, like when Apple entered the marketplace and mobile. No, they were not a mobile company, but now they are one of the biggest mobile companies in the world, right? So, and I did that. One of the things I mentioned at the time was quantum computing. I said, you're going to have to seriously even look at it now because you get the lead on it. I remember at the time, people thought I was crazy, right? Because they thought I was an outlier and it's going to be 2100, 2200 or something before it became serious. But, I just mentioned, I just did a Forbes article, or I interviewed 11 people to get their predictions. And I don't think anybody said it's not going to happen. And it's not going to be 100 years from now. I think people thinking that it's going to be in the near to medium term, and you know they're going. So, what are your views on that? Do you think it's like the pseudoscience which people thought a few years ago? Or do you think you know this is a reality, and then you know we really do have to look at it? Right? So,
Yeah, I mean, I guess my take on it is I expect there to be some interesting use cases for it first. You know, I don't think, I mean, you know this, but you know, we're not going to have quantum computers in our cell phones or anything like that, right? But there will be, I expect that there will be some interesting use cases for quantum computers in the not too distant future that will be, you know, better than what you can do with a classical computer. And the thing that I think I don't know the answer to is exactly what that's going to be, right? Is it going to be in drug design? I think that might be a little bit farther off. Is it going to be in factoring? You know, what is it? What are going to be those first few areas where it's really showing, you know, a sort of a preeminence compared to sort of what you can do classically, and then where are we going to go from there? And like I said, I think from where I sit, I think, you know, broadly defined quantum design is what would be amazing. You know, if you could, rather than having these really expensive experiments to try to find new materials that are superconducting, you can actually just simulate the system on a computer and be like, oh yeah, this is how you do it, blah, blah, blah. You know, we're going to, or whatever. I think that would be a really interesting use case. But, you know, if I had to guess, you know, maybe within 20 years, we're really going to have quantum computers doing things that classical computers can't do. And then once that happens, it might then be exponentially fast before we're just, you know, doing everything that way. But you know, I think we're all kind of guessing there, but we definitely want to make sure we're contributing as much as we can to that very exciting area.
you know, it's interesting. I mean, I did 2 recent interviews, one with Humble, who's the director of their Quantum Institute, and it's related to the Department of Energy, and it does work at Oak Ridge as well. And then Dongarra, who won the Turing Award for his work in supercomputing, and they already have the exascale, which is a billion calculations per second. And in our conversations, we thought, oh, is Zeta going to be theirs? You know, which is 1,000 billion billion, and there's this whole sort of tension that you can run these things in quantum-inspired algorithms, new ones coming out. So every time somebody claims some test case, which is not practical, but just a set case, right, as test case in quantum supremacy or quantum advantage, and then some other research group says, hey, we can run that on us.
I can do that. Yeah, right. I can do that classically. Yeah. It's sort of this interesting, it's an interesting race. I mean, one question I have for you, and then I think about, you know, Moore's law, and what we're doing with classical computers, you know this probably better than I do, but you know, the energy requirements as we keep scaling up are non-trivial, right? And we're going to go back to the climate discussion. You know, what are people saying in that space in terms of quantum computing? I mean, how are we going to continue to sort of accelerate our ability to process data and do all the things we need to do in a data-driven world without, you know, getting into trouble with the energy requirements for some of these things?
You know, that's a really good question. So, you know, I just did an interview with the Sovereign Fund of Canada, and they launched something called the Deep Tech Fund, and they've invested in quantum, but they're also invested in photonics, and because photonics has a lot of promise, not just in quantum, but in classical computing as well, where you can get a much better efficiency, maybe even get a reduction in energy. There's these new 3D stacking technologies using resistive RAM, where you have a deep integration between the CPU and internal memory, using this new resistive RAM technology. And in fact, I've got an interview coming up with Philip Wong at Stanford, and he's probably the most foremost expert today on this next generation, where you can get maybe a 10-fold power decrease, and yet it well integrates with things like AI embedded in the chip, and you get this really rapid, radical performance increase as well, because of this tight integration on the chip, almost like a system on a chip, you know. And you're getting, you know, scaling even sub-micron, right? So, you know, this idea, or nanometers, I should say, not sub-micron, but nanometers. You know, you used to say 17 and then 10 or 7 and then 5 and then 3, and now they're even smaller. And this, I think this 3D idea is really interesting. And in fact, I'm an investor. So we're looking at what are some of these plays that are occurring. So I don't think Moore's law is going to be a problem, because there's so much work going in all these other novel areas that look really interesting, even novel materials that look really interesting. And so I don't think it's going to be a problem.
That's fantastic. That's amazing. It makes sense. As soon as you say 3D, it's sort of like, oh, okay. We have a whole new dimension to play with, right?
Yeah. So, we live in interesting, exciting times. Now, I want to mine some of the other work you're doing and then get your look at. So I had an interview with Roger Penrose. This is really interesting. In fact, we had him at AI for Good. He was the opening keynote, and at the time, Roger didn't know that he had a 20-minute time limit. So I met him in advance the day before, and I said, Roger, can you present what you're going to do in 20 minutes? And so we sort of brainstormed and what we was going to present. In fact, I read all the sort of the major bulk of his research on the plane in advance of the meeting, and I thought it was really interesting. And then I had dinner with him for about 10 hours at another conference where we were both keynotes, and it was really interesting, his ideas. And he got a Nobel, right? For his work. And you're in cosmology, and he's in cosmology. So, what are some of your ideas in that space, where it's going? And it'd be interesting. Roger has some really interesting ideas as well.
Right.
And so, where we are today, and exascale supercomputing and deep learning and machine learning can have an impact on all that. There's the James Webb telescope is going to give much deeper insights than the Hubble, of which you were a Hubble postdoctoral fellow at Harvard University. So you really understand that element, but you're also then, moved to be chair of, this like the projects that are going to be run on this James Webb Space Telescope. So a lot of ideas, combining that together. Where are we in cosmology today? Where are we going to be?
Where are we going?
Where are we going? And what about some of the Rogers ideas? Or do you think that he's kind of in his own space?
Well, I think the stuff, let me save the stuff that Roger is thinking about for a little later. I mean, I'm going to talk a little bit about the kind of cosmology that I do, which is a little bit distinct from the kinds of things that Roger does. So I really think of myself as a physical cosmologist. I'm pretty close to the ground when it comes to trying to figure out what observations are telling us to sort of begin to inform our deeper ideas about what the universe is made of and where it's going and what the fundamental constituents are. So I think right now in cosmology, we have a pretty good idea, at least sort of descriptive idea, of what the universe is. But what we've discovered is a little weird. The universe, as we understand it now, has a total mass energy density that is dominated by something that we call dark energy. Right. And the other sliver is dark matter. And that's different. And then there's a tiny little bit, about 1/6 of the mass energy density of the universe is basically everything in the periodic table, everything we've been talking about today. So the rest of the universe is made up of this stuff, which is actually distinct and at some level kind of not particularly well understood physics. What this is telling us is that the universe is richer and deeper and, governed by, things and forces and particles that are very, very different than what we can easily interact with as humans. And, it shouldn't be, one thing is you hear this initially, and sometimes the immediate reaction is, that sounds crazy. How is that possibly true, that there's all this mass out there that's different than anything we can detect? But, what's to say that this species of ours, us, we should have evolved to detect everything in the universe? We detect the things we need to detect. We can detect visible light with our eyes because our sun shines visible light. We can't detect infrared light with our eyes. And it took us a long time to figure out there even was infrared light. And now we have to build big telescopes to study infrared and build cameras to look at things in the infrared, right? So there's all kinds of things out there, including photons of weird wavelengths that we can't easily interact with. There's neutrinos that are out there that we can't easily interact with, but that we've discovered. And what cosmology is telling us is that the universe itself, the construct of the universe, is much stranger than the stuff we've evolved to interact with. Now, the deep questions today are, what the heck is this dark matter? The thing that I'm trying to figure out, what is this dark matter stuff? And what's up with this dark energy? They're two different things. The dark energy is what's driving the universe, not just to expand, but to accelerate in its expansion. And the dark matter is the stuff that remarkably is dominating the clustering gravity of the universe. And without it, we don't think any galaxies or planets or us would exist. We have a lot of evidence that it's there, but we don't know exactly what it is. Now, we have a standard kind of understanding, sort of a basic model that does really well, that sort of lays out the percentages and the characteristics of the dark matter and dark energy that I described to you. But what's interesting with Webb right now is there's some initial observations that happened right when the telescope turned on that were very surprising and difficult to interpret in the context of this picture of cosmology that I just laid out to you. So the very first time the telescope turned on, we saw some stuff we didn't understand, right? And oftentimes it's like this, right? When you look somewhere you never looked before, oftentimes you discover something you weren't expecting. And so it could be that as we continue to study the universe with with Webb, and measure how fast it's expanding, and begin to look at the very earliest galaxies that formed after the Big Bang, it will tell us that, okay, something very different must be going on with how dark matter is clustering in the early universe, or how dark energy is making the universe expand right now. So the things that I'm trying to work on are sort of close to that. It's sort of looking like in a very kind of empiricist way. Our models say this should happen. We observe this other thing to happen. What does that mean in terms of our understanding of how the universe works? And let's build off of that sort of very observationally driven stuff in the context of, we think general relativity is correct right now, but maybe it's not. We'll see if those observations are going to tell us it's broken. We think we understand the laws of particle physics, the way particles should interact, but maybe that's going to break at some point. It's trying to utilize these kind of cosmological observations to inform our understanding of this universe that we cannot see, most of which we cannot see directly. We have to study it indirectly with these telescopes and colliders and things.
So maybe we'll explore just a tiny little thought experiment.
Sure.
Imagine a parrot sitting on a fence, and that parrot is not contemplating quantum gravity collapse and quantum mechanics and cosmology and dark matter and so on. And that's because of constraints, or what I believe are the constraints within that parrot, right?
Mm-hmm.
Or corvids, which are quite advanced, sort of a type of birds that are out there that can problem solve. But then I think of humans. We have 85 billion neurons. We have 125 trillion synapses, and if you include this idea of microtubules, maybe we have an octillion kind of computational capability, but that there's a finite limit. And then you introduce this idea that, and it's kind of like Fenwick's idea that we're a lens, so we're a filter. We only can conceive of what we can conceive. So maybe in a cosmology sense, we're that parrot on a fence, and it requires some kind of computational understanding that we're just at level 1 and you need level 100 to be able to. Do you ever think of that? I should say that we just don't have the mental capacity unless we use some kind of language or a large machine learning model that's in the hundreds of trillions, and then it can identify patterns that we just can't even conceive of. All right.
Yeah, it's certainly possible. I think there's an Einstein quote that, something to the effect that the hardest thing to understand about the universe is that it's understandable, right? I got it wrong, but it's something like that, right? It's sort of what I was alluding to before, that look, like we're this species that evolved on this planet, over the last couple 100,000 years, and somehow we're equipped to sort of not only ask these questions, but at least come up with some answers to where we are in the universe and begin to construct models that explain what we see. I think the scientific process so far is we really have constructed these models leveraging mathematics, which is sort of an amazing tool that was either discovered or invented, depending on the way you think about it. And these days, I think you're exactly right that we are leveraging what we can do with really sophisticated computation, the sort of artificial intelligence, these sort of algorithms that are somehow able to learn, and maybe we'll learn even faster in the future. We leverage all the tools we can to develop these models that, they're sort of like the shadows on the wall of the cave. I mean, we've imagined to create these models that predict what the shadows look like on the wall of the cave, but where we're actually seeing the reality is a deeper, really interesting philosophical question. And so, a question becomes, what could we ever do? Could we ever, are we only ever just constructing a model that does better and better at sort of explaining what we see without getting to fundamental truth, whatever that means? Or is fundamental truth the only way we can even define fundamental truth is that through models that we can predict what's going to happen, and then we see it happen, and that's as good as we can do in a very kind of utilitarian sense. I think that's a really deep question. I think if we do see advances in artificial intelligence that transcend what we're doing now, way beyond pattern recognition and speed of calculation, that can truly learn in ways that are useful, you could see it. But then, one question that that you might ask is, what does it mean for us to understand something? If I have a code that I can run that predicts what's going to happen, does that mean I understand it? Do I understand it in a way that I find fulfilling? Or do I need to understand it in some kind of human way that allows me to gain sort of deep intuition for it? And then I kind of understand it deeply in my heart and then can apply it, right? I mean, that's kind of a philosophical question, but I think as we move towards a world where we're really reliant on the sort of the machinery and the sort of simulations to predict things, then the question of what is the role of the scientist and the human in that? What are we learning from that? If all we really have is a black box computer program that tells us what's going to happen, what are we doing? So for me, I think about that a lot. Like when I run a simulation and at the end of the day, a galaxy is there that looks about like a real galaxy, does that mean I understand how that galaxy formed? Yeah. Well, my computer seems to understand it, but do I understand it? And then what can I do? How can I learn from that, right? So I think this is something that I think about a lot.
Yeah, and we're in the perfect time for all of this and the realization of all of this. This is the last question, and then you're probably sensitive to time. You probably have something coming up in a few minutes. So I guess the final question is, what are your recommendations to the audience?
Oh, well, I mean, what do you mean in terms of what to read, what to think about, anything?
Open platform.
Recommendation. I mean, I'll go back to what I started with before. I do believe that a really deep understanding of sort of the core science of things is going to be important for the world moving forward. Beyond a descriptive sense, really at sort of the both qualitative and quantitative understanding of why we think things are happening. So if you're worried about climate change, I'll be honest with you that the science of climate change is not that complicated. A lot of people say, well, I'm not a climate scientist, I don't know what's going on. There's some basics to what happens with greenhouse gases that an intelligent person can sit down and think about for a little while and begin to understand what the repercussions are. It doesn't mean you understand everything. But I guess a recommendation of mine is to dig in a little bit to the details beyond the sort of surface level of what's happening, to think about sort of the core science that might be driving things that are important in our lives. Because I think not only that's where sort of understanding comes, that's where nuance lives, but that's also where maybe the breakthroughs are going to live. And of course, you always have to work out the complex realities beyond the sort of basic science behind things. But my deep recommendation is to sort of center yourself on the sort of deeper understanding of the core phenomena, rather than trying to start at the surface. If you're at the surface of something that's interesting, try to sort of burrow down occasionally to figure out what's really happening at the bottom.
And then I'll conclude just with some additional data about you, James. You're a Chancellor Fellow. You received 2 UCI Celebration of Teaching Awards. You're a Fellow of the American Association of Advancement of Science, and ... You've done so much. So my recommendation with your really thoughtful recommendations is that I recommend the audience follow your work in UCI and the awesome stuff that's happening there. So,
well, thanks so much. This has been a wonderful conversation, and I really appreciate the opportunity. It's been fun. Can't wait to do it again sometime.
Okay, take care. Thanks a lot.
Okay, bye-bye.
Bye.
Thank you for listening to the Brand Called You videocast and podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for the Brand Called You.